Welcome to the first tutorial of the course. If you have really seen the questions and tried to solve them, you might actually see them as a revision of what we have learned so far, or even revision of what you have learned until now, until the organic chemistry course, which is the very basics of molecular bonding, the very basics of atomic orbitals and structures of different molecules. But my understanding is that our foundation should be strong so that we can build up really good as we go ahead and look in the actual course material. So, for now let us really get quick and really comfortable with such questions. The first question here talks about identifying the hybridization of each atom in the molecule. It also talks about identifying the geometry around each atom, and it asks you to identify in which orbitals are the lone pairs situated, right. So, now let us start with the first molecule, that is nicotine here, and what we have here is, let us start with the carbons. So, all of these sp2 hybridized carbons. Why I am saying sp2 hybridized? Because they are double bonded, right, they are forming 3 sigma bonds and a pi bond. Now, the third sigma bond might not be really visible, but that is right there. We do not draw hydrogens as we already saw, right. So, it is forming 3 sigma and a pi bond, and that is sp2 hybridized, right. So, all of these carbons are sp2 hybridized. Are there any sp3 hybridized carbons that are forming 4 sigma bonds? The answer is yes. I have these 3 carbons here, this fourth one, and then this methyl group, this methyl group. So, all of these carbons here, the green ones, are forming our sp3 hybridization, because they are forming 4 sigma bonds, right. Now, the question arises, which other element here is actually sp3 hybridized. So, now there are 2 nitrogens in the molecule. One of the nitrogens here is forming 2 sigma bonds, has a pi bond and has a lone pair, whereas this particular nitrogen here is forming 3 sigma bonds and a lone pair. As you can see, this particular nitrogen, the other nitrogen which is forming 3 sigma bonds and a lone pair, the situation is very similar to that of having 4 sigma bonds. So, you can see that it is sp3 hybridized, but do not always fall for that trick. Every time you make 3 sigma bonds and a lone pair, the nitrogen need not be just sp3 hybridized, and we can look at some of the examples in the next one. I am going to go over an example where that is not the case. But right now, if you really see this nitrogen, that lone pair is kind of locked on that nitrogen. It cannot move around because it is bonded to another 2 sp3 hybridized atoms. When that is the case, you can be assured that the nitrogen is sp3 hybridized. So, this one here is sp3 hybridized, whereas the one that is double bonded is actually sp2 hybridized. Okay. So, now we have kind of jotted down the hybridization of each and every atom in the molecule. Okay. Now, the second part of the question talks about identifying the geometries around each atom, and sp2 hybridized centers, as we know, are trigonal planar. They have 120 degrees bond angle, and they have the pi bond going up and down, that is above and below the plane of these 3 atoms, right. Whereas sp3 hybridization is tetrahedral in nature, 109.5 degrees bond angle. So, we are kind of sorted on the geometry, right. Now, let us talk about the orbital in which the lone pair is residing, right. So, let us look at the sp3 hybridized nitrogen. Now, its ground state electronic configuration is 1s2, 2s2, 2p3, right. In order to show that it does sp3 hybridization, we move one of these electrons up, right. So, it goes to the excited state electronic configuration, and then we combine these 3 p orbitals and one of the s orbitals to really form 4 sp3 hybridized orbitals, right. So, that is what the theory says. So, in this case for this sp3 hybridized nitrogen, the lone pair resides in the sp3 orbital, right. That is really easy. Now, let us go to the tough part. Now, let us talk about the double bonded nitrogen and let us figure out where does that lone pair reside. Okay. So, for that I am going to get rid of this part and we are going to talk about the sp2 hybridized nitrogen. We have 1s2, 2s2, 2p3, that is our ground state electronic configuration. Then as we talked about, we go to the excited state electronic configuration by moving one of these electrons up, and then in order to form sp2 hybridized orbitals, what you need to do is you need to combine one of the s and two of the p orbitals together to form 3 sp2 hybridized orbitals. If you look at this particular nitrogen, it is forming 2 sigma bonds. Now, sigma bonds are typically formed when you have a higher s character, because there is a better overlap happening. So, s character gives rise to sigma bonds. So, when you have these 2 sigma bonds, you can say that the 2 orbitals are sp2 hybridized. The question lies where the lone pair is sp2 hybridized or whether the lone pair really resides in the p orbital, which remains unhybridized throughout the process. If you really look at this particular molecule and if you look at the geometry of the molecule, the lone pair is such that it is away from the molecule, it is pointed in the direction that is in the same plane of the molecule, right, but it is also going away from the molecule. So, if this is the molecule here, the lone pair is kind of directed outside of the plane of the molecule. So, the lone pair also really resides in the sp2 hybridized orbital, okay, right. So, the nitrogen has 3 of the sp2 hybridized orbitals. With 2 it forms the nitrogen carbon bonds and the third one is used to occupy the lone pair, whereas the one electron that does not take part in hybridization really forms the pi bond with the other carbon. So, that is how it forms that carbon nitrogen overlap to form that pi bond. So, this is sp2, this is sp2 hybridized, right, and whereas the lone pair is now in sp2 hybridization and the carbon nitrogen pi bond takes place because of the electron in the p orbital that does not hybridize from each of the nitrogen and carbon. So, when this molecule has to hybridize, it is going to take one of the s and two of the p's to form that sp2 hybridization. One electron is going to remain unhybridized, right. So, not necessarily the lone pair is always in the p orbital, that is not always the case. In fact, you have to look at the molecule's geometry in order to figure that out. Now, let us look at this particular example. This is dopamine. Dopamine is the molecule that really is the key molecule that makes us happy. So, this is the happiness molecule we have here, and if you look at the hybridization of each atom, first let us go over that. All of these carbons which are double bonded and a part of the benzene ring are sp2 hybridized, right. Bond angles of 120 degrees, they also are forming 3 sigma bonds and a pi bond. So, we are good with that. These other 2 carbons and this nitrogen here, these 3 atoms are sp3 hybridized, right, because they are forming 4 sigma bonds. So, the carbon and the nitrogen, they are forming 4 sigma bonds. Nitrogen again is kind of having either 3 sigma bonds and a lone pair, right. So, that is very similar to having 4 sigma bonds. Again, the nitrogen's lone pair is kind of locked on that nitrogen, it cannot give it to the carbon next to it. So, we are safe to assume that it is sp3 hybridized. Now, let us look at the oxygens here. This is the tricky part. If you look at this particular oxygen, it may seem like it is forming 2 sigma bonds and has 2 lone pairs, right. So, the oxygen here has 2 sigma bonds and 2 lone pairs. If you really think about it, this is very similar to that of water. Water also has 2 sigma bonds on that oxygen and also has a lone pair, but in the case of water, it was sp3 hybridized. Now, here is the tricky part. Think about the resonance structure. Is the lone pair locked on that oxygen? If the answer is yes, then okay, then it is really sp3 hybridized. But if it is not, if you can move that lone pair from that oxygen to the next atom and really create a new resonance structure, then that lone pair has to be in an orbital that can be moved to the next atom, right. Such that, let us now look at the hybridization of this oxygen. We have the ground state configuration as 1s2, 2s2, right, 2p4, right, that is the ground state electronic configuration. Now, I will draw the excited state electronic configuration, and that is 1s2, 2s1, right, something like this. Okay. Now, the real question arises that when the oxygen exhibits hybridization, it wants to have that lone pair such that it can put in those electrons into the benzene ring, because we can clearly draw a resonance structure such that that OH can donate inside the ring. So, herein this becomes sp2 hybridized, because that lone pair has to be in the p orbital, which is kind of perpendicular to the plane of the ring such that it can easily be donated into the ring. So, you have 1s2. Now, I am going to do 2s and 2p, but I am going to combine one of the s's and two of the p's to form the sp2 hybridized orbitals, and one of the lone pair does not take part in hybridization. So, it remains in the p orbital, right, the unhybridized p orbital. Okay. When you have these sp2 hybridized orbitals, one of them will form a bond with hydrogen, the other one will form a bond with carbon, and one of the lone pairs will actually stay in the sp2 hybridized orbitals. Okay. But in all, if you really see that the hybridization of oxygen, it is not like sp3, even though the oxygen is forming 2 sigma and 2 pi bonds, right. It is not like sp3, but it is more like sp2. So, just do not be tricked by just remembering the number of the sigma and pi bonds, but rather look at whether that particular oxygen or nitrogen can it really form a resonance structure, because remember resonance hybrid always exists, right. It is not like oxygen is sp3 at a time, then once it donates electrons into the ring, then it becomes sp2 hybridized. That is not the case, because the molecule is going to exist as a resonance hybrid. So, in order to exist as a resonance hybrid, the right way for that oxygen to exhibit is having an sp2 hybridization. Okay. So, be careful when you are solving questions like this. The next question really talks about drawing resonance structures and resonance hybrids. So, now let us draw a couple of molecules and their resonance structures. Again, when you are drawing resonance structures, remember that you are allowed to move only the pi electrons or the lone pair or the charges, right. Charges also the negative charges, right. So, in this case I am going to draw a resonance structure of this particular molecule, when oxygen with its lone pair is going to give electrons to this particular, the first carbon. But remember that as this oxygen shifts the lone pair on that carbon, that particular carbon is already forming a double bond with the other carbon and it cannot just accept a pair of electrons. So, what it does is it breaks the carbon-carbon double bond and gives the electrons to the next carbon. So, what you have here is a negative charge on this particular carbon. Okay. We can continue doing this. This particular lone pair can now form a bond between carbon numbers 2 and 3, right. So, if I go 1, 2, 3, 4, the lone pair can now go between carbon numbers 2 and 3, but again carbon number 3 is already forming a double bond. In order to accept a pair of electrons, it cannot really form more than 4 bonds. So, it has to break one of the bonds and the bond it chooses to break is the pi bond. So, what you have here is this. So, what I have is this particular resonance structure. I can again put this one back here and I can continue doing this kind of rotation, but when we draw resonance structures, please remember that in order for the carbon to accept, it cannot just accept it, it has to break a bond in order to accept the new pair of electrons. Now, let us do this one example here. In this case again you have the resonance structures for this particular molecule. Now, the nitrogen can donate its electrons here and that will make this particular carbon move its pi bond from that double bond in between, right. This will give rise to this particular structure. Right. I can continue doing this particular electron pair can go here and that can go up and you can form this structure. You can again bring back the lone pair of electrons and go in the reverse direction. So, that is when you start from the nitrogen, or I can start from this oxygen from the other end. So, the oxygen, let me just redraw the molecule here. The oxygen here has a pair of electrons that can be moved here and this goes here. So, right, that is one of the possibilities. Again I can draw one more structure such that this can go here and that goes up. So, what I have here is these are all the possible resonance structures for this particular molecule, and when you are drawing resonance hybrid, make sure that you are looking at where the double bonds are, whether they are present in all the resonance structures or whether they are present in only some of the resonance structures, then you have to draw a partial dashed line, right, or a partial line. Okay, let us draw this imidazole molecule here. Now, in the case of imidazole, remember that I can draw this particular lone pair giving into the ring. That will cause this nitrogen to be positively charged. So, always remember to put those formal charges. It is very important that we do not forget our formal charges, right. As a result of which this carbon nitrogen bond is shifted on this nitrogen, and that is the case. I can continue moving it, I can put it here and this will move the electrons back here. So, that will form this particular structure. Okay. So, you can draw resonance structures of many molecules. Herein you have an enolate ion. Enolate again you can draw it such that the carbon lone pair can be pushed towards the carbonyl group and you have this particular resonance structure. right. So, all of these are possible and you can go ahead and draw them. Now, let us quickly revise resonance hybrid. So, for example, if I want to draw the resonance hybrid of this enolate ion, what I need to do is I need to look for the bonds that are constant, that is the bonds that do not change. This is the sigma bond structure that did not change throughout all the resonance structures. Now, I will draw dotted lines wherever there are double bonds in only some of the structures and not all the structures. So, that is that case. So, there is a partial line between carbon oxygen and the other carbon carbon. You also look at the lone pairs, you give them, right, and you also give a partial charge, because in one of the cases the oxygen has a negative charge, but the other structure it does not have, whereas in the same case the first structure has a carbon that is negatively charged, but the second structure does not have. So, what we are going to do is we are going to give a delta negative on both of these atoms. That is how my resonance hybrid looks, right. Now, let us draw it for this molecule. This is a benzene ring. So, we have a lot of charges to move around. Now, remember in this particular molecule, the carbon that is bonded to the benzene ring is positively charged. It is a carbocation. In this case, we have to move electrons from the ring back to the carbon, right. And what we are going to do is we are going to move these electrons here. Okay. Let me just say 1, 2, 3, 4, 5, 6. As the electrons between carbons 1 and 2 move towards that outer carbon, what happens is that carbon number 2 is now short of 2 electrons, because what happened was it lost a bond. So, as a result of which it gets the positive charge, right. Whereas, in the next case, when this moves, the carbon number 3, 4 double bond, when it moves to carbon number 2 and 3, that carbon number 4 is going to get a positive charge. Always think about which is the carbon that lost a bond, right. So, when carbon number 3, 4 moves from that position to 2, 3, 3 is really just shifting one of its bonds, right, but the fourth carbon here, it really loses a bond. So, that gets the positive charge. I can go on doing this, I can draw one more structure, and now carbon number 6 will get a positive charge, right. So, all of these are possible structures. I can go back to the first structure by pushing electrons this way. See, one thing I always want everyone to remember is that when you are drawing resonance structures, please do not draw more than 2 lines at a time, or more than 2 curved arrows at a time. It gets highly confusing. So, it is much better to just do 2 steps at a time, and that way you do not miss out on a resonance structure. So, especially when we have to draw a resonance hybrid, if you miss out on a particular resonance structure, your hybrid is going to look incomplete. So, it is better to just push 2 arrows at a time and no more than that. Okay. So, now I want to draw the hybrid of this particular atom. Now, I want to draw the hybrid of this particular molecule, and then let us now look at 1, 2, 3, 4, 5, 6, right. These are the bonds that do not really change. Of course, I have not drawn the carbon hydrogen bonds that are kind of there, but we have not drawn them anywhere. Now, let us look at the pi bonds. So, the pi bonds are there in between 1 and 6. It is there in some of the resonance structures, it is not there in some of the other resonance structures. So, it gets a partial line. Same goes for the pi bond between 1 and 2. So, it is present in this first structure, but it is absent in the second structure. So, that gets a partial line. Same way, if you see, the pi bonds between carbon and carbon are kind of such that they get a dotted line that I have represented with this blue color. They get a dotted line between all the structures. So, the system is really in conjugation, meaning the double bonds are kind of getting interchanged in the resonance hybrid, such that all of them coexist partially at the same time. Now, let us look at the positive charges. So, in the first resonance structure, the carbon that is outside the benzene ring has a positive charge, whereas in the second one the charge moves on the second carbon, in the third one it moves on the fourth carbon, and then it moves on the sixth carbon, and that's how it is moving around, right. So, when I want to give a partial positive charge, I will look at the carbons that have it. So, in the case here, the CH2 outside will have a delta positive, carbon number 2 will have a delta positive, carbon number 4 will have a delta positive, and carbon number 6 will have a delta positive, right. So, all of these are the delta positive carbons that are present, right. If you see in any of the resonance structures, you do not have a positive charge on the third and the fifth carbon or the first carbon. So, in our resonance hybrid also, we do not want to put a partial positive on those carbons. So, 1, 3 and 5 do not have charges, the rest of the molecules will have a partial positive in the resonance hybrid. So, the analogy towards resonance hybrid is that you can imagine that it is something that exists, right, but the corresponding contributing resonance structures do not exist as themselves. So, it is like having a rhinoceros. So, rhinoceros are have a horn, right, and they have a very thick skin. So, you can imagine that rhinos are kind of a combination of dragons which have very thick skin and unicorns which have a horn, right. But both unicorns and dragons are kind of fictionary figures and they really do not exist, but rhino, which is a combination of both of them, really exists. So, that's how you want to think of resonance hybrid, is that that is what it exists as and not as these individual resonance structures. Okay. So, let us look at some more examples. Herein we have an amide. In this amide, the nitrogen can put electrons here and we can really have an overlap such that the carbon and nitrogen form a double bond. And the oxygen and carbon form a single bond. So, in fact, the amide bonds that exist in nature are such that the carbon nitrogen bonds have much more double bond characters, because the particular resonance structure here is quite stable if you think about it, because the octet of each element is really complete and also the carbon nitrogen overlap is kind of high, right. So, what you have is that amides also show a good resonance contribution of this particular resonance contributor and can really show a partial double bond characteristic between the carbon and nitrogen. The next question really talked about drawing the Lewis structures of these molecules. So, what I am going to do is I am going to do some of them. So, let us do the first one, which is H2SO4, which is a common mineral acid, right. So, when we look at H2SO4, what do we have? First step while drawing Lewis structures is that we count the total number of electrons. So, the total number of valence electrons for this particular molecule is 2 for the hydrogens, 6 for the sulfur and 6 for the oxygen, but I have 4 of them. So, 6 into 4, that is 24. This will give me a total of 32 electrons, right. 32 electrons meaning I have 16 electron pairs, right. So, now when I draw the structure, I have to fill in 16 electron pairs into the molecule. Again, first things first, we have gotten to the number of electrons. Now, the next thing we want to do is we want to place a skeleton of the molecule such that the atom that can form the maximum number of bonds is at the center of the skeleton. So, we want to put sulfur in the middle because sulfur can really expand its octet, and then I want it to bond with the 2 oxygens, or rather 4 of the oxygens, and 2 of these other oxygens I want to bond with the hydrogens, right. So, that is kind of the skeleton I want. The reason why we chose hydrogens bonding to the oxygen, because I knew that H2SO4 is an acid and you need a proton. So, right. So, it needs to be attached to the oxygen such that it can be easily removed in an acid base reaction, but that is, even if you did not have that, you could still draw one more structure and still try to come up with a possible scenario, but this is the one that I am going to work with now. This is our skeleton structure. Now, if you think about it, how many electron pairs have we attached? So, we have 1, 2, 3, 4, 5, 6 we have used so far. We have to use 10 more electron pairs. Both the hydrogens have satisfied their valencies. If you really think about the 2 oxygens that are here and here, which are attached to these hydrogens, have also satisfied their valencies, they are forming 2 bonds each. Then these other 2 oxygens, we really need to fill in their valencies. So, what I am going to do is, I am going to give the 2 electron pairs here to form that bond. Okay. Now, is it such that the octet of each atom is complete? The answer is still no, because we are yet to place the lone pairs. So, right now what I have used is 8 electron pairs. Now, I need to put 2 more. So, I am going to put them here, here, here and here. This really satisfies the valency and the octet rule of all elements. So, what you have here is the structure of H2SO4 becomes this. Right. So, we have really taken care of the molecule such that we have used all 16 electron pairs, and we have also completed the octet for each atom in the molecule. So, that is the structure of H2SO4. Now, let us do one more compound, that is NaN3. So, sodium azide is also used in biolabs a lot. So, sodium azide, let us now look at the Lewis structure. So, whenever we have an ionic compound, we first give it the charges. So, it will be Na plus and N3 minus or azide ion, right. So, what we are going to do now is we are going to look at the azide ion and figure out the structure of that. Nitrogen has 5 electrons in the outermost shell or the valence shell. So, the total number of valence electrons is 5 into 3, that is 15, right. But remember that negative charge, that needs to be added for one more electron. So, then you have 16 electrons present that I need to take care of. 16 electrons, that will give rise to 8 electron pairs. Okay. Now, when I want to draw the azide ion, I can look at it such that the 3 nitrogens are kind of, there is no other atom. So, it is very easy to come up with the skeleton structure, it is the 3 nitrogens, but that really takes care of just 2 electron pairs. So, now let us put 2 more. So, that is 4 electron pairs. Now, let us put 5th one, 6th one, 7th and 8th. So, I can draw the skeletal structure like this. So, we have taken care of all the 8 electron pairs. But if you really think about it, what about formal charges, right? Remember, we always want to think about formal charges. The middle nitrogen, it is forming 4 sigma bonds, right. So, if you really think about it, its valency is 5 minus the number of electrons that it is sharing, right. So, how many electrons really belong to the nitrogen? Only 4 of them. So, we have it as 5 minus 4, right. So, the formal charge on this particular nitrogen will be plus 1. So, the middle nitrogen will have a positive charge. Now, if you look at this other nitrogen here, 5, which is the number of valence electrons of the nitrogen, minus how many electrons are in the lone pair? 4, plus the number of electrons that are in the bonding pairs divided by 2. So, that will be 2. So, that will be total of minus 1. So, the other nitrogens actually have a charge of minus 1 each, right. So, what you have here in fact is that the sodium azide has this particular Lewis structure, okay, whereas both the nitrogens on the outside of the azide group are negatively charged, the internal nitrogen is positively charged, and together if you really think about the molecule, you have an ionic bond between sodium and azide. Let us take one more example, which is of BH3. So, this is really simple, right, because boron is going to have 3 electrons in the outermost orbital and then the 3 from the hydrogen. So, total it gets to 6 electrons, that is 3 electron pairs, right. So, now let us put the central atom as boron. It is going to form 3 bonds with the 3 hydrogens. Everything looks good so far, and if you think about it, we are done with using our 3 electron pairs. But think about whether each and every atom in this molecule has the octet complete. The answer is no. Boron here has only 6 electrons around it, right. So, 6 from the 3 BH bonds. Boron here is electron deficient. So, when this particular molecule reacts in chemical reactions, what you really see is that the BH3 is such that the boron is kind of ready to accept electrons from other molecules, and boron here really acts as a Lewis acid. And so, this is also something you must have learned before, Lewis acids and Lewis bases. So, Lewis acids are the molecule that accepts a pair of electrons in a chemical reaction, and such that they have the vacancy for that particular electron pair to be accepted. Boron here can accept a pair of electrons, and in fact, let us write down a reaction between BH3 and NH3. So, BH3, which is our Lewis acid, and ammonia, which is our Lewis base, right. Right. So, Lewis base here, the ammonia, is going to put its electrons towards the boron, because there is a vacancy. Boron really wants 8 electrons around it. So, what gives rise to is a coordination bond between nitrogen and boron, because both the electrons are really coming from nitrogen and boron is not contributing any electrons towards the bond. So, what you now have is this particular compound, which is a Lewis acid Lewis base complex that is formed. Okay. We are also going to look over Lewis acids and bases when we go over the chapter of acids and bases, but I thought it would be good to include an example for a Lewis structure wherein the central atom is actually short of the required number of electrons for the octet. Okay. Let us take the last example, which is C3H6O. Okay. Whenever we have a compound like this, let us first figure out the number of electron pairs that we have. In order to do that, we first calculate the number of valence electrons that are present in the system. So, for carbon we have 4 electrons, and I have 3 of these carbon plus hydrogen, we have 6 hydrogens, and oxygen, there is 1 oxygen with 6 electrons. So, what do you have here is 12 plus 6 plus 6, that is 24 electrons, right. Now, if you calculate 24 electrons, what you have is 12 electron pairs. Okay. So, we have 12 electron pairs around it. Now, if you think about it, let us draw a skeleton such that the 3 carbons are kind of in one line, okay. And you can draw the 6 hydrogens such that they are forming a bond here. The middle carbon is forming a bond with the oxygen. If you really see the skeleton structures, we have taken care of 1, 2, 3, 4, 5, 6, 7, 8, 9 electron pairs, right. So, if you really see, we have taken care of the 9 electron pairs and we have 3 more electron pairs to put, and those 3 electron pairs can actually go as a double bond between the oxygen carbon and the 2 lone pairs on that oxygen. This really takes care of the octet rule for each element. This also fulfills our 12 electron pairs. But remember, this is not the only structure that is possible. So, let us now draw one more structure which will really satisfy the rules. So, now I can put electrons between the two . This is also a valid Lewis structure of the same, because I still have every atom completing an octet and I still have the right number of valency for being fulfilled for all atoms. This is a valid structure. I will tell you one more. So, now I can have, right. This also is a valid structure, right. I can go on writing more structures. So, I can even draw a Lewis structure for the same molecule wherein the oxygen forms the ring. So, there are so many possible ways in which you can really draw this particular molecule and its structure. The reason is that why I want to go over all of these possibilities is that when you are looking at Lewis structures, you can arrive to a solution that seems very logical, that fits all the criterias, and that is, in fact, it could be one of the right answers. All you need to check in order to identify if your answer is right or wrong is that are all the electron pairs satisfied, are all the atoms in the compound have fulfilling octet rule complete, and also have you paid attention to the formal charges that may be there in the molecule. As long as you have done that, you can really arrive at a number of possible solutions and each one of them would be right. Now, in order to figure out which one is really the right molecule amongst all of these, I may have to do some chemical tests. So, for example, if it is a ketone like acetone that is shown there, it will do the reactions of ketones, or if it is an alcohol that we drew in the second time, it will do the reactions of alcohols. If it is an epoxide, it will do the reactions of epoxides. So, just based on the molecular formula, you can still arrive to a number of possible outcomes and you will have to do chemical tests to identify which one is the right answer. Okay. So, that was it for the first week. We will meet next week with our very first organic chemistry chapter, that is the chemistry of alkanes.